So we've got a small group of us so far. No challenge question today. So instead, at this time, I want to ask you guys if you have any questions about that assignment that you got last time, the where you've got to draw the shapes and come up with the sorry, just one sec. Come up with the sequence for it. Were there any questions about that assignment? Do you know which one I'm talking about?
Yeah, that one was actually pretty straightforward. I felt it wasn't that hard. I have it here. I don't think I finished it fully because I had to go do stuff.
Yeah.
Am I really loud?
Nope.
Ruben says I'm being super loud. I'm sorry.
I don't think so. No.
It was kind of straightforward. I felt like I realized after what I had done was the simpler way, but I thought that it was different. So okay. I did diamond, and then it would just kind of multiply and keep on multiplying, right? And yeah. So I started I realized it was just the number was going to be multiplied by itself, like if that makes sense. So It was 4, then it would be 16, then it would be 32, and so on and so forth. And then I got to a number that was super big, and my calculator just kept saying error, and I was like, oh man. Yeah. So I wasn't able to fill in all the way to, I was only able to make it to T12.
Okay. Maybe not T30.
At T30, I just wrote the infinite symbol because the number was just getting so high that it just keeps going.
Yeah, that's pretty interesting because it's interesting that you can start with maybe a fairly simple pattern, but if you keep going with that pattern, you might end up
it starts out as one shape, right? And then you just put the shape inside of it and make it into 4 shapes, or maybe it's 3 shapes, whatever it is.
Right.
And then it just continues on from there. And then 2 becomes 4, 4 becomes 16, 16 becomes 32. And then once you're at T30, it's just a huge number.
Yeah, yeah. So
it almost looks like a solid color after a while.
Oh yeah.
How thin the lines would have to be.
Because you're filling everything in, and yeah.
I did for the example is it all had to be n would equal the number by itself. So t would equal t times n, so the number that was your last number. So kind of like the Fibonacci sequence, the number before it is times, and then the next number times.
I see.
So
yeah, okay, all right. It sounded like you were talking about these numbers, 32, 16. So and maybe 64 was next. I don't know if you recall.
Well, it would have been 32 times 32.
Oh, so it's really huge numbers. Oh, okay.
Yeah.
Yeah, I see.
It went 16 times. Sorry, it shouldn't have gone to 32. It should have been 16 times 16. And that number times itself. That number, 16 times 16, comes out to 100 and.
Is it 256?
Yeah, I think so. I think it's 256 or 254.
Let's see. 16 times 16, 256. Yeah.
256,
then you would have to go.
And then 256 times 256, then it just,
Yeah, 65,000.
And then you times 65,000 by itself, and it just
gets huge.
Keeps on going. And by the time I was getting to 8 was the last number I think I was able to actually get.
Yeah.
And that I really couldn't find the calculator I would need, or the amount of division I would have had to, or the multiplication I would have had to do would have been very crazy.
Yeah.
And it was that was in the trillions. I'd have to do a trillion number.
Right.
And that's a lot of multiplication to do on paper. That's a couple sheets of just getting it all to go, because I don't have, the Apple calculator isn't very good, to be honest.
Right.
It's okay.
It's not bad.
It doesn't get huge.
I'm trying to think if there is, because there might be a way to calculate these, just like how we saw with, I think we looked at this sequence. No, not that one. This one here. And it was interesting because in both in both classes, someone mentioned, Kate, we're increasing by 3, we're increasing by 5, we're increasing by 7. So there's that one pattern, but there was also this pattern that, okay, it's 1 squared, 2 squared, 3 squared, oops, 4 squared. So I wonder if there's some sort of pattern like this that could be used to describe yours, Jonah, like 2 to the power of n, or 3 to the power of n, or 2 point, well, probably not 2 point something, but yeah. All right, thanks for sharing, Jonah. Anyone else have any questions? Drayden, welcome to class. You missed just the beginning where I said there was no challenge questions. So Drayden, we're instead, if you've got any questions about this assignment here, you can ask. So yeah, are there any other questions about this assignment? We're doing okay. All right, good. Let's keep going then. We're moving on to the last section of this chapter. And at the end of this chapter, what I'd like to do is have a quiz. All right, my aim is to make it like 5 or 6 questions. So short. I don't want to make it too challenging, but I do want to test that you know how to solve systems. Okay, these are linear systems, and maybe a little bit about arithmetic sequences and series. Okay, so so we'll maybe after the break I'll point out a few questions from the practice area. What do they call it? The chapter review that you could prepare for. So maybe I'll look at 5 or 6 questions. I'll choose some, and those will be the questions that I base the quiz questions on. For today, we're looking at arithmetic series. And a series is simply the sum of the terms of a sequence. So we said how a sequence is just a list of numbers, sometimes with a pattern, sometimes not. So this is a sequence. A series, then, kind of the corresponding series here would be 1 plus 1 plus 2 plus 3 plus 5 plus 8. We simply add up those things. So in this case, we can actually do this addition, and we get 2, 4, 7, 12, 20. Oh, interesting. All right. So that's what a series is. We add up the terms of a sequence, and there's interesting patterns that can be show up because of that. We're also going to learn about sigma notation, which is a different way of writing those series. All right, here we go. This is a classic series here. Can you think, is there some sort of pattern to each of these terms here? Look at these numbers. Is there some sort of pattern? What do you think?
I think Rachel's in the car.
Oh, sorry, I didn't.
No, wait, maybe she's not. Never mind.
So, sorry, Drayden, you were going to say something, right?
The numbers add themselves. So like for 2 plus 2 equals 4, 4 plus 4 equals 8, 8 equals 16.
So if we look at these numbers here, you're saying if we add 2 plus 2, we get 4, etc. Right? 4 plus 4 is 8. Yeah, good. And so this is, yeah, exactly. We're adding that amount each to the denominator, each one. These are also the powers of 2. So exactly like what you're saying, because we're adding the same amount each time. But if we think about 2 to the power of n, right? So this first one here then is 2 to the power of 1. This next one is 2 to the power of 3. 2 to the power of 3, 2 to the power of 4, etc. Right? So this is a classic series. What do we get if we add these all up? What's the sum of these things if we add them up?
Hey, Mr. Boyer.
Yeah.
Rachel can't hear us.
Rachel, you can't hear us? Rachel, are you in a car right now? She can't hear.
Yeah, I'll message her to message the group.
Okay, well, sure. Then I'll leave you in charge of communicating with Rachel for now. In the meantime, we will just continue on with class here. So we actually can add these all up, and instead of kind of finding that this way, we can use something like Wolfram Alpha to do this calculation. So here I go. You know, we can just type this in 1/2 plus 1/4, etc. And we see that if we add those up, can you guys see this okay on your screen? Yeah. Okay. If we add those up, our exact result is 15/16. So we can actually do this addition here. I really like this. Wolfram Alpha is also offering viewing it in terms of these pie charts to show, hey, if we add 1/2 of a pie plus 1/4 of a pie plus 1/8 of a pie, etc., we're going to have 15/16.
What was this website called again?
This is Wolfram Alpha. Wolfram Alpha. Do you see it up there, Hunter?
Yeah, I do. Thank you.
Sure, you're welcome. It's very it's very powerful. It can be a little daunting sometimes, but there's lots of stuff that it does really well. I'm trying to troubleshoot for Rachel here, but I don't know. Maybe I'm not sure what to do about that. All right. So this series can also be written in something called sigma notation. So this and these two things are equal. These are communicating the same thing, okay? In fact, like this one on the right here is telling us the answer one more time. So I'm just going to block that just to make it very clear that these two things here are identical, okay? So sigma notation is just another way of writing the sums of things. Sigma sum, right? Finding the sum of things, okay? We notice that pattern that I talked about where we had 2n in the denominator, that shows up right here, right? So let's look at some other examples of sigma notation here. Okay, so sigma notation. Don't worry about this index of summation. Let's cross that out here. But sigma notation says a few things. Here at the bottom of this sigma symbol, we put our first value of n. This is like the value that we're starting with. At the top, we put the last value, okay? And then here, we always put the formula for the terms. So if I were given this, this sigma here, this sigma notation, I'm going to start with a n value of 1. So I've got 4n here. First, it's going to be 4 times 1. And then I continue up the ladder, right? If I start with 1, my next one is going to be 4 times 2, right? What's next? So folks, I'm looking at this as my general formula here, right? I started with an n value of 1, and I'm increasing each time. So what's the next thing that I'm adding here?
Would it be 4 times 3?
Yeah, exactly. So we're changing our n value each time, right? 4 times 3, 4 times 4, plus 4 times 5. And where do I stop?
4 times 6.
4 times 6, exactly, that one there. So I'm adding up all these terms here. This is what sigma notation, this is how I interpret this, this sigma notation here. So this is going to be 4 plus 8 plus 12 plus 16 plus 20 plus 24. And let's see, can we do some quick math here? That's 40, 64, I believe. So we can actually do this summation. We can do this addition here. Okay, are there any questions about that so far? Here's another look. This is a much simpler formula. If we look here, this is just n. It's not 4n. We're starting with an n value of 1 and ending with an n value of 4. So all we're doing is, well, we replace n with 1, and then we move on to the next term, right? n is 2. Move on to the next term. So it's 1 plus 2 plus 3 plus 4 in this case. All right. Sigma notation we can also do in Wolfram Alpha. So this is where I mean, take a look at what I typed in here. We type in this thing that says sum of something, and then we say n from 1 to 4. So we notice that we're doing the same sort of thing, right? We're saying that we're finding the sum of something. So this is 1 over 2 to the power of 1 plus 1 over 2 to the power of 2 plus 1 over 2 to the power of 3, and finally 1 over 2 to the power of 4. And we can see that this works out to be the same series that we saw earlier. 1 over 2 to the power of 2 is 4, 1 over 8, and 1 over 16. We saw before that it was 15 over 16, and if we add those up, we would get the same thing. All right. What's neat about this is that we can start playing around with our n values. So instead of going from 1 to 4, maybe we go from 1 to 8, right? And now this becomes a much more complicated sigma notation. Or maybe instead of 1 to 8, we go 3 to 8, right? And Wolfram Alpha can calculate it very quickly. Okay. We can even, instead of 1 to a number, we can go from 1 to infinity. And so that's my question. Is it possible to find the sum of an infinite number of terms? Right? So we talked about how we could have infinite sequences. Well, we can have infinite series as well. Infinite series. All right. So let's say we do some sort of pattern like 2 plus 4 plus 6 plus 8 plus, and then we keep going. Can we find the sum of that? What do you think? Is there going to be a sum of these numbers, 2 plus 4 plus 6 plus 8, into infinity? Will there be an answer to that?
Wouldn't it just be infinity?
Yeah, so many of these series will just sum to infinity, right? Something like this. We talked about this one here, 1 plus 2 plus 3 plus 4. You know, we talked about how there's that controversy of this one. Is it equal to negative 1 over 12, or is it equal to infinity? Well, it's not that one, okay? However, let me ask you a different question. Is it possible to find like a real number, like find a number that is not infinity for an infinite series? What do you think?
Isn't it like negative 1 over 12 or something?
Well, that was that 1 plus 2 plus 3 plus 4.
Okay.
Yeah, which we said in like the best way to describe it is that it actually does go to infinity. But is there one, let's say we could add up an infinite number of terms following a certain pattern that does equal a number, like 200. Is it possible?
But you'd have to add like negatives, right?
You could, yeah. Maybe you add, like, maybe there's some sort of pattern where you go 1 plus negative 2 plus 3 plus negative 4. And you could add some of those numbers. Well, Wolfram Alpha lets us do some things like that. So like we could, let's look at this. Let's say we're looking at the sum of n values from 1 to infinity. So I'll type that in. Let's have a look at the sigma notation here, right? If we interpret this, this means we're starting at an n value of 1. So here's our formula. We're going 1 plus 2 plus 3. And it says here the sum diverges. The sum diverges. That means it doesn't have a real solution. It doesn't have a real value that it adds up to. We could try, I think you were, let's see, negative, let's try negative n squared. So if we did something like this, we're starting with an n value of 1. I guess that negative sign doesn't do much of anything. 2 squared plus negative 3 squared. This is this series here, and it's saying this diverges as well. However, do they all diverge? Can you imagine if there's any type of series that doesn't diverge, that does have a value that it adds up to? All right, folks, to help illustrate this, I'm gonna read you a story. Okay, it's story time. Hey, are you paying attention? Are you? Okay. This is a story of Zeno's paradox. All right. It's a famous paradox. It's written just in one way here, and you can just kind of read along if you want, or you can just listen. You can close your eyes if you like. Okay. This is a paradox that Zeno came up with. All right. The tortoise. So it's between tortoise and Achilles, a famous runner. The tortoise challenged Achilles to a race, claiming that he would win as long as Achilles gave him a small head start. Achilles laughed at this, for of course he was a mighty warrior and swift of foot, whereas the tortoise was heavy and slow. How big a head start do you need? He asked the tortoise with a smile. 10 meters, the latter replied. Achilles laughed louder than ever. You will surely lose, my friend, in that case, he told the tortoise. But let us race if you wish it. On the contrary, said the tortoise, I will win, and I can prove to you by a simple argument. Go on, then, Achilles replied with less confidence than he felt before. He knew he was the superior athlete, but he also knew the tortoise had the sharper wits, and he had lost many a bewildering argument with him before this. It sounds like a smart tortoise, eh? Suppose, began the tortoise, that you give me a 10-meter head start. Would you say that you could cover that 10 meters between us very quickly? Very quickly, Achilles affirmed. And in that time, how far should I have gone, do you think? Perhaps a meter, no more, said Achilles after a moment's thought. Very well, replied the tortoise. Now there is a meter between us, and you would catch up that distance very quickly? Very quickly indeed. That's Achilles talking. And yet, in that time, I shall have gone a little way farther, so that now you must catch that distance up, yes? Yes, said Achilles slowly. And while you are doing so, I shall have gone a little way further, so that you must then catch up the new distance, the tortoise continued smoothly. Achilles said nothing. And so you see, in each moment, you must be catching up the distance between us, and yet I, at the same time, will be adding a new distance, however small, for you to catch up again. Indeed, it must be so, said Achilles warily. And so you can never catch up, the tortoise concluded sympathetically. You are right, as always, said Achilles sadly, and conceded the race.
I don't think that's mathematically true. Wait a second here.
So, but it makes logical sense, right? So this is the paradox, because it makes logical sense in one way, but not in another. So yeah, what do you think? Like,
It makes sense in one way, but at the same time, it's a freaking tortoise, so like he'd be going super slow. So technically, he could easily catch up to the tortoise. Maybe if it was a different comparison of something a tad bit faster but slower than a human,
Yeah.
that would listen.
Yeah. So it's interesting. So like there's almost like some sort of fallacy in like there's something that the tortoise is saying that that's wrong. What is it that's wrong about what he's saying?
He's not taking into consideration that he's going much slower and that he will have passed him by the time. Yeah. He's not taking everything into consideration.
You're right, he's not. But, you know, he is admitting that he's slower. He's saying that, like, okay, like, you know, when you catch up to me that first 10 meters, you know, I'll go another meter. And so you've still got to catch up to me. When you catch up that 1 meter, I'll still have gone a little way further. So you'll still have to catch up to me. And so he's saying, you're always going to be catching up to me.
But if you think about it, what he was doing was the tortoise wasn't trying to actually beat him in a race. He was trying to beat him in a battle of wits.
Mm-hmm.
And kind of prove a point there. But it was kind of just a joke story in the end of it. Like I get the story it's trying to say for the paradox, but
Mm-hmm.
it's definitely like kind of just a humorous little, doesn't actually work, because if the hare wanted to win, or Achilles wanted to win or whatever, he could just pick a different distance instead of running the 10 meters to catch up with him. Just
Mm-hmm.
run 15, and then he's already in front of him, and
Right.
he can continue at a pace faster than the tortoise and win the race.
Right. Good. Yeah, Jonah. So that's kind of exactly what we're what the paradox is. You know, like the tortoise is looking at these snapshots. So first he's looking at that 10-meter snapshot, and then that 1 meter snapshot, and then the next one is very short, right? So he's looking at these snapshots, and he's imagining that, hey, if we just like look at these shorter and shorter, these time intervals that are getting shorter and shorter and shorter, we'll never see a moment where Achilles will pass the tortoise. But of course, in real life, we're not focusing on those shorter time intervals. Instead, we're seeing this thing happen all at the same time, kind of thing. Yeah. So here we've got an interesting series. We've got 1/2 plus 1/4 plus 1/8. We'll talk about that in a little bit. Why don't we talk about that after our break? So we're going to set a timer for 8.5 minutes. He is a class clown, isn't he?
That's what that was. I was like, what on earth is going on?
All right, folks, we're going to keep going here. You ready?
No.
I knew, yeah, I shouldn't have asked the question. Yeah. All right, well, get ready. We're moving on. You got Zeno's paradox. And Zeno's paradox is interesting because it's kind of like, well, let's see. Rather than tackle Zeno head on, let us pause to notice something remarkable. Suppose we take Zeno's paradox at face value for the moment and agree with him that before I can walk a mile, I must first walk a half mile. And before I can walk the remaining half mile, I must first cover half of it. That is a 1/4 mile, and then an 1/8 mile, and then a 16th mile, and then a 32nd mile, and so on. Well, suppose I could cover all these infinite number of small distances. How far should I have walked? 1 mile is what they're saying, right? After I cover all those half and half and half of that and half of that and half of that, you will have covered 1 mile. And so this is interesting. This is saying that if we add up all these numbers, you know, according to this pattern, we should get 1. We should get 1. Do you agree? Do you agree with that? In other words, yeah, okay, sure. In other words, this sequence here, I think I can just go plus ... It's kind of like a universal thing for let's keep this going. If I say I'm going to keep this pattern going, the sum that they give, what they say is that we're going to a value of 1. And I really, really like this. Where did it go? There it is. I really like this pie chart symbolism for this, right? So like we can see that they're adding up a half plus a quarter plus an eighth plus a 16th. Each piece is getting tinier and tinier and tinier. If we add them all up, we're getting pretty close to a whole pizza pie, right? We're getting very close to a whole pizza. If I kept this pattern going, if I, added one more tiny 1/32 of a slice, we would fill in a part of that gap there, right? And if we could keep making smaller and smaller pieces of pizza, we would get a whole pizza, right? So this is really interesting because we're adding up an infinite number of numbers, right? We're adding up an infinite number of numbers to get one, right? Add up an infinite number of numbers to get one. I think that's very interesting. All right. So we can have infinite series add up to a finite number. Just to kind of illustrate something that's kind of interesting, we said if we keep this going, it equals 1. If we try a different pattern that looks similar, 1/2 plus 1/3 plus 1/4 plus 1/5, if we add all those up, we actually get infinity in this case. So very similar, but we end up with infinity. All right. I think I wanted to, yeah, we got story time 2 here. This is this one that I'm remembering. There's this famous mathematician Gauss, right? And there's this story about him that maybe is true, maybe is not. But when Gauss was a student, he would always ask his teacher questions, and they would be like pretty poignant, pretty good questions, pretty difficult questions. And he would always finish his homework really quickly, and so he would be bothering the teacher. So there was one day where Gauss was bothering his teacher. So his teacher said, "Okay, Gauss, just go over there, and what I want you to do, I want you to add up all the numbers, all the natural numbers up to 100, right? Up to 100. I want you to add them all up, and then when you're done, come back and show me, right?" And so the teacher thought this would take him, at least 15 minutes or something. But Gauss came back in a minute, and he said, "Okay, I found it. It's 5,050." And to the teacher's astonishment, Gauss was correct. He had added them up really quickly, and so they asked. So the teacher asked Gauss how he did it, and this is an important lesson that we can take away for today's chapter. All right. So what I want you to do with me, along with me, okay, I want you to imagine that we're taking this series and we're adding them all up, right? So we're going to call this, sure, we'll call it S. This is some series S. Well, I could take that same series and I could write it in reverse. So in reverse, it would be 100. Let me just kind of give myself a bit more space here. So I'm going 1 plus 2 plus 3 plus ... plus 100, okay? I could write these in reverse. I could go 100 plus 99 plus 98 plus ... And what would be my last one here?
1.
1, yeah, okay. So this is what Gauss did, presumably. He kind of figured out, okay, I can do this kind of work. And then if I add these two up together, that would be 2s, right? It's going to be double what the sum actually is, but I'm going to go 101, 1, right? 1 plus 100 is 101, okay? Plus, what do we got here? 2 plus 99, what do we get?
101.
101, okay? And then how about this? 3 plus 98, what do we get?
101.
101, okay? And then we're going to go ... And at the end here we go 100 plus 1, that's 101. So if we do this, it's kind of like finding the average. But if we do this, we're adding up the first and the last together, And all of these will be the same. Okay, so now this becomes a pretty simple multiplication thing. We're going to go 2s, right? So this is still doubled. 2s equals 101 times, how many of them are there? How many terms? How many terms are there, right? So how many times are we adding up 101? 1, 2, 3, ... How many?
100 times.
100 times, exactly, right? This is our number of terms. Our number of terms is 100. So we're saying that 2s is equal to, that's a s, not a 5. 2s is equal to 101 times 100. So let's see, 2s equals, well, that just becomes 101,100. No, I was right the first time. Okay, 10,100. And if we wanted to find s, then we just divide by 2, and we get 5,050. Look at that. All right. So this is the work that Gauss did, and this sort of pattern works with this list of natural numbers that's increasing by 1, but it will work with every arithmetic series as well. So say we had a different type of series that was 3 plus 4 plus 5 plus 6 plus 7, let's make it a little more interesting. Let's say we've got 7 plus 10 plus 13 plus, what's next, 16. And I'll just go up to here, okay? I'll just go up to here. This is only 5 terms, so it's not huge. Well, we could do the same sort of thing. 13, 10, and 7. If we add them all up, we see that this, again, this is 2s. This is equal to 26 plus 26 plus 26, etc. Right? All these are the same. So we're going 26 times how many terms? It's 5 and divided by 2. So we're going 26 times 5 divided by 2. What do we get? I don't know. What do we get? 13 times 5, 26, 52, 65. 65, I think. Okay. So this works with all arithmetic series. So, excuse me. So in your textbook and right here in front of you, we have these 2 very nice formulas that help us find the sums of series, arithmetic series. So here's one in blue, and here's one in purple. We can kind of see how this first one, this is what we were doing. We were taking A1 is the first term, right? A2 is the second term, or sorry, the last term. So we're adding up the first and last term, and then we're multiplying it by the number of terms, divide by 2. You can see that's what we're doing there. There's this one other one as well that is very similar. This, though, the difference is we have n. We need to know n for that, and we need to know d. So maybe this is when we don't know the last term. So let's see a couple of these in actions. We're going to do some examples from the textbook. I'll just do them up here on the board. We'll kind of look at them here. The first one asks, so this is example 2, find the sum of the first 25 terms of, and then our pattern is 11 plus 15 plus 19 plus ... Okay. So, so we're asked to find the first 25 terms. How we're going to start with this, we're going to try to find as much information as we can. Okay, so in our textbook, we're often dealing with A and D. Okay, So A being the first term, D being the common difference. What is our A value here? What's our first term? Hey, look. Which number comes first?
11.
Yes. Okay, good. Now, I didn't think that would be a difficult question, but it took us a little while to get that. The more difficult question here, what is our common difference? Okay, so how much are we increasing by each time?
4.
4, right? Positive or negative?
Positive.
Yeah. Okay, good. So we have our A value, we have our D value. We've also got this number here. What variable will I use to represent 25? So I'm going to add it to my list here. Something equals 25. What would it be if we kind of keep to our common math language here? So we've got an A and we've got a D. Let's look at our previous slide for a second here. Okay. We have these 4 things here. Okay. What would that 25 be?
A to N.
A to N, well, that is actually the value of the last term. So we don't actually know what the value of the last term is. Instead, what we know is let's do undo. Instead, what we know is that this is the number of terms. So this is actually our N value here. All right. Now, because we don't know the last term, we cannot use this equation, okay? Because we don't know this important piece of it. So we're gonna have to use this one. It's a little messier, but it's okay. So undo. So I'm gonna write that out. I'm gonna write out our equation, which your textbook has just slightly different because it's n over 2 times, we've got 2a plus n minus 1 times d. Okay, so we'll plug in the things that we know. We know that n is 25. 25 over 2. 2 times our a value is 11. Plus, I'm just going to get us started here. Plus our n value again here is 25 minus 1, and our d value is 4. Okay, so if we complete this math, we'll find that value. So let's see, we got 25 over 2. This is 22 plus this becomes 25 minus 1 is 24 times 4. Okay, we've still got 25 over 2. 22 plus 24 times 4, that's 96. 96 plus 22 is 118. And then we can do that there to get 1,475. I didn't do that math. I copied it from the textbook. Okay. So if we add that up, if we add up those first 25 terms, that's what we would get. We would get that value there. Okay, stop me if you have any questions. We're going to move on to another one here. It says find, this is example 3, find the sum of 7 plus 10 plus 13 plus ... plus 100. All right, so in this case, now let's start to list the things that we know. So we for sure know A and D. What's our A value here?
7.
Great, thank you. I love that I heard 2 people real quick answer that question. Okay, how about the D value?
100.
Well,
sorry.
that's
3.
3, yeah. But what did you just tell me, Ruben? What is 100? We've seen it called A N.
Terms.
Yeah. the value of the last term. Your textbook actually gives us the variable L, which stands for last term. So you might hear, or you might see it L, you might see it AN, but it stands for the last term. So this one we can use our simpler sum formula. Sn equals, we're going n divided by 2 times A, our first value, plus L, our last value. Okay, so we're going, oh, actually we don't know n, do we? Ah, that's right. Okay, so we need to do one thing before that. We need to find our n value. That's right. So for this, we're borrowing a formula from the previous chapter that looks like this. Our certain value is that first value plus n minus 1 times d, right? This is what we use to find the value of a certain term in a sequence. So we know that that is 100. We know we're starting with 7. We don't know what our n value is, and we're going times 3. So we can subtract 7 here. We get 93 equals 3n minus 3. I did distribution here. Okay. And then we got 96 equals 3n. And then finally, n equals 32. Okay, we divide it by 3. Now we can use our sum formula. We're of n over 2 times A plus L, our last term. Okay, so we've got 32 terms that we had to figure out. We know that our first term is 7 and our last term is 100. Okay, so it's 16 times 93. 1,712. All right, folks, we're going to get started soon with our homework here. I do feel like we gotta do at least 4, and there's one other thing we got to talk about too. So yeah, let's do example 4. I'm gonna bring up the textbook here actually, so just give me one moment here. Page 266. All right, so example 4 here, we're evaluating, it might be hard for you to see, but this is k equals 1 to 100. And then we have this formula here. So we're doing sigma notation. As part of this solution, your textbook is finding, certain values. So starting with finding the very first value. Well, that's going to be when we have a k of 1. And so they do, like, this k value is going to be 1. So we're able to find that our first value in the series is going to be 3. This is our L, right? So they're finding the last value. They're going up to 100, so they're able to find that it's 201. They can see that the common difference is 2 because we're increasing by 2 each time. And then, of course, the number of terms is 100. So they did a little bit of work to find those things. First, the first term, the last term, and so on. And so we can use either one of our formulas to find the sum. By the way, you will be using those formulas, and you can find them on page 265. Here it is. Okay, so you've got 2 formulas here. One that I'll underline in green, and one that I'll underline in blue. Okay, you see how there's 2 formulas there? All right, last one. Because this is introducing a new term. This is saying find two arithmetic means. Two arithmetic means between 8 and 29. This is basically asking a question, hey, if I went 8, comma, blank, comma, blank, comma, 29, what are the two numbers that would fill in this sequence, right? So it's asking for two arithmetic means. Okay. And so for this, we know our first term is that. Our second term, we're just adding a common difference to it, right? See that? We're going to go 8 plus whatever the common difference is. And for that third term, we're going to add that common difference again. So our task then becomes trying to find what that common difference is. And so what your textbook is doing, it's setting up this equation that we're going 8 plus 3d must equal 29, right? We're saying that, hey, this is going to be plus d. We're going to add another common difference. And when we add a third common difference, we're going to get to 29. So there's 3 of those. 8 plus 3d equals 29. So let's solve for d. It's 7. And so we can go then. Now we know that our d value is 7. We know that d plus 7 is 15. And 15 plus 7 is 22. Okay. Questions? No questions. If you do have questions, let me know. I'm going to show you what your homework assignment is. It's right there. All right. You've got a couple of word problems. There you go. You can go and get started. And we'll spend maybe 20 minutes together here working on that.
Mr. Bohr, how would we find n for c again? 'Cause I don't really remember.
So this is 1c.
Yeah.
1c. Yeah, so we would have to use the formula that we learned in the last chapter. So this is where, hey, if we are looking for a certain, we've got this equation that we learned. A(n) equals, let's see if I can remember, a plus n minus 1 times d, right? So we learned this formula. In this case, for 1c, we know that we know a few things. We know an equals 77. That's our last term. We know our first term is 2. We know our common difference is, looks like we're increasing by 3 each time. And we don't know the number of terms, question mark. So yeah, we can use this to solve for that. We'll plug in 77 equals 2 plus, we're trying to find that n, and then our d is 3. So we can solve that equation to find n.
Okay, thank you.